Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be discussing on the topic carbon and its compounds. We are going to be looking at the allotropes of carbon. So, the allotropes of carbon is another subtopic that has also been repeated in the topic when we are discussing structure and body. So the allotropes that we are going to discuss, you notice, is a repetition. So you can go back to that video and check it out and get to see some of the properties we may not be able to mention in details. So we'll look at the allotropes of carbon in this lesson and the amorphous forms of carbon, and then we'll tackle a few questions. So carbon is the first element in group 4 of the periodic table. It has an electron arrangement of 2.4, and then it usually forms covalent bonds in most of the compounds since it's an nonmetal. So carbon actually does not ionize, it doesn't lose electrons, it actually shares electrons. So it naturally occurs as allotropes of carbon, that is the graphite, diamond, and fullerenes. And it also occurs as amorphous forms of carbon, or later on we'll refer to them as the impure forms of carbon. This is in coal, peat, charcoal, and coke. And then also carbon is found in carbon dioxide, which is around 0.03% of volume in the air. So first you're going to start on the allotropes of carbon. So allotropy is the existence of an element in more than one form in the same physical state. Existence of an element, this element exists in more than one form, but they are in the same physical state. As you can see, all of them are in solid state. So the different forms are usually called the allotropes, and we have naturally occurring allotropes like diamond and graphite. So when we look at diamond and graphite, you're going to look at some of the properties of diamond and some of the properties of graphite. We may not be able to go in the same details we did when we are doing structure and body, but you can go back and check that out in structure and body. So diamond is usually a colorless, transparent, and shiny crystalline solid. It has a giant tetrahedral structure. So you will notice when we were doing the structure and bonding, we were able to discuss how diamond is bonded. And remember, one carbon atom is bonded to 4 carbon atoms, and the structure goes on and on and on and on until it forms a very large structure. It's tetrahedron in structure. And you can see this is just an example, but we did the details in structure and body. It has very high melting points and boiling points. The reason why it has very high melting points and boiling points because, first of all, it's closely packed. These are the carbon atoms. They are very closely packed in a giant tetrahedron structure, and they have been joined by strong covalent bond. And the key thing is a strong covalent bond. First of all, there is a packing. They are very closely packed with strong covalent bond. So these bonds require a lot of heat to break. And then they have a very high density, or they are hard. Actually, diamond is one of the hardest substances. This is because of the uniformity of the covalent bonds between the atoms throughout the structure. They are very uniform, very uniform. And then they are poor electrical conductors because they do not have any delocalized electrons. We say the 4 valence electrons in carbon are bonded fully by 4 other carbon atoms. It is used to make jewels. It's also used in drilling and cutting metals because of how hard it is. And then the graphite is usually black and soft and slippery crystalline solid, as you can see from the image. It has a giant hexagonal planar structure. So if we were to draw the structure of a diamond, it looks something of this sort. And then remember, also for the diamond, it has very high melting point. The reason why it has high melting point as well is because also the carbon atoms are closely packed as well in a giant hexagonal planar joined by strong covalent bonds. Even though we have weak van der Waals forces between the layers, it does not mean that their melting point and boiling point is going to be low. The fact that the atoms are the ones that we are trying to separate when we are heating, it's going to be very high melting point because we are breaking strong covalent bond, not the van der Waals forces. And then it's usually soft, which means that it has layers and the layers can slide over each other because of the weak van der Waals forces, as I've shown in the image above. They are good conductors of electricity because they have free valence localized selection. So we say only 3 of the 4 electrons are used in bonding. So the one that remains is the one that we refer to as the delocalized electrons. It is used to make lead pencils because the layers slide over each other and they are left on the paper. And then it's used to make electrodes because of its conductivity, and it is used as a lubricant because of the layers. And then we also have fullerenes. Fullerenes are usually synthetic allotropes of carbon. They are usually found in different shapes. It can be spherical, tabular, or elliptical. An example is 660. So that's how fullerene looks like. So we go to the amorphous forms of carbon. These are the impure forms of carbon. And examples are like charcoal, soot, and coal and coke. Usually contain small amount of graphite, but they do not conduct electricity regardless. This is because the graphite crystals are usually arranged in an irregular manner. So you can't say they should conduct electricity because of the graphite and because graphite conducts electricity. No. Because of the way they are irregularly arranged, it's not able to conduct electricity. And then amorphous carbon, especially charcoal, has the ability to absorb gases and liquids. So the amorphous form, that is charcoals especially, is used to make gas masks because they absorb gases. And then charcoal is used to absorb colored impurities in sugar in refining industries. And then carbon black is mixed with rubber in the manufacture of tires as a filler to improve tensile strength and reduce wear and tear. So you can be taught to mention some of these uses of these amorphous forms of carbon. So make sure you are able to remember at least the most common one is the charcoal being used to absorb gases in gas masks, and also charcoal being used to remove impurities in sugar refining. So let's look at a few questions. So one use of graphite is used to make lead pencils. We also said it can be used to make lubricants, and also it can be used as an electrode. Both graphite and diamond are allotropes of element carbon. Graphite conducts electricity whereas diamond does not. Explain. So we said that graphite, only 3 of the 4 electrons in carbon are used in bonding, leaving one delocalized electron that can conduct electricity, while in diamond all the 4 valence electrons are used in bonding. So state one use of diamond, it's used to make drilling bits. It can also be used to make jewels. What is allotropy? So this is the existence of an element in more than one form in the same physical state. And then graphite is one of the allotropes of carbon. Name another element which exhibits allotropy. So the other element that exhibits allotropy is actually phosphorus. We have the white phosphorus, we have the red phosphorus, and you'll see this one especially on the one that is used to make matchbox is usually the red phosphorus. Also sulfur, as you discussed in Form 3, we have the two allotropes of sulfur, monoclinic sulfur and rhombic sulfur. So explain why graphite is used in making pencil leads. So we said the reason why it is used to make pencil leads is because graphite has layers which slide over each other due to the weak van der Waals forces. So when you are writing, these are the layers that usually are left behind on the paper. Diamond and graphite are crystalline forms of carbon. State two non-crystalline forms or the amorphous forms. So we have coke, we have coal, and soot. So that brings us to the end. So later on, you're going now to go into carbon, and then in the also preceding lessons, you look at the oxides of carbon. So see you in the next lesson.